Hi everyone, thank you so much for joining us today for our guest speaker session. We have with us Aurko. Aurko is a member of technical staff at Microsoft AI. Prior to Microsoft, Aurko has worked at Meta AI. He was a research scientist at Google DeepMind and Google Brain. Aurko has completed his PhD from Georgia Tech and bachelor's and master's from IIT Kanpur. Thank you so much, Aurko, for joining us today, and I'll hand it over to you.
Sounds good. Thanks for inviting me and uh, giving me this platform to share my work. I guess the way I was planning to go was I made like a bunch of slides for the high level ideas, and then depending on the interest level and the level of technical details that people want to go into, we can also sort of go through parts of the paper. So let me try to share my screen. Is this visible?
Yeah.
Okay, cool. So, right. So our work is called Fast and Simplex, Two Simplicial Attention in Triton. And this is with a bunch of amazing co-workers and co-authors at Meta, University of Texas, and former collaborators from Google as well. So Tim Chow is at Meta, or used to be at Meta. Sai was at UT Austin. Stygia, Jiachao, Xiaodong are at Meta. Manzel and Rohan. Rohan is a longtime collaborator from Google. All right. All right. So the motivation of this talk is sort of, if we think in terms of the higher level of high level trends of where the world is headed in terms of the trends in AI and machine learning, what we see so far is that all around us, the news of new data centers being built, new compute clusters being built. So essentially, this is a picture of the Stargate data center that OpenAI is sort of building. And what we can see is that data centers, essentially after the invention of transformers in 2017, and more recently after ChatGPT in 2023, it's really sort of an arms race in terms of, people are really throwing the kitchen sink on building more and more compute capacities in data centers. This is not just OpenAI, but Meta, Google, Microsoft, and all the big hyperscalers, right? On the other hand, we see that high quality data, like tokens that actually have useful signal in terms of content or in terms of things that tell us something new about the universe, or they teach us something new about the world or the laws underlying nature, right? Which is what we sort of associate with intelligence in terms of so the way I would understand intelligence is trying to understand some deep correlations or patterns that explain the underlying data or that explain the underlying reality that we sort of live in. And high quality data, of course, is not going to keep up with the growth of our compute clusters, right? Because it takes some level of insight, work, and things of that nature before one sort of can put something out that actually can teach the model something new, right? And so this is sort of an ongoing area of investigation, right? So in terms of how do we address this problem of data being the bottleneck, right? So once we start training on the whole internet, what can we do about the lack of high quality data? And there's been different proponents of people propose synthetic data and model generated data and so on. But I would argue that none of these have successfully panned out or been demonstrated to actually teach the model something new. And by this, I mean the frontier models. So of course, you can use synthetic data for distillation, but to reach the frontier and to keep pushing the frontier, I think it's not entirely clear whether synthetic data is the way to go, right? And then the other sort of scientific approach that dominates the current paradigm is what we call neural scaling laws, right? And this is sort of the guiding principle behind how we scale transformers. And the idea is that it's sort of an empirical observation that says that when we look at the training loss or the validation loss, or loss per data sets, what we see is what Kaplan et al. And Hoffman in the Chinchilla paper, what they observed is that this law, the scaling law, sort of what it proposes is this loss is scales as a power law in the number of model parameters and in the number of tokens, right? And to put it more precisely, one can formulate this as sort of this equation where we have the loss parameterized as the number of parameters and the data set, or the number of tokens. And here, in fact, one can add many more parameters, right? And all of you could potentially, for example, try to estimate your hyperparameters in this way, right? And what this equation sort of posits is that the loss actually is sort of modeled as a generative process, where the generative process is trying to capture the irreducible entropy of the underlying data. So E is the irreducible entropy of the text. It could be the irreducible entropy of let's say natural language, or depending on your data distribution, it could be the entropy of physics text or math text or whatever, right? And the second term essentially says that the second two terms, the two terms essentially say that we are not able to capture this generative process accurately. So the first term is an error term due to the finiteness of our model parameters. So we get something like A divided by n to the alpha, where n is the number of parameters. So the reason we say this is sort of a power law is because it's n raised to the alpha. So alpha is sort of the exponent that is estimated in those papers. And then we have B divided by D to the beta, where D is the number of tokens and so on. And here you could potentially add several other factors that you think are influencing this generative process. But the most important factors are typically the number of parameters and the number of tokens. And really the goal is to reach the irreducible loss by whatever that means of text, right? And one can sort of see that the underlying assumption here is that you need both infinite model parameters and both infinite data to actually ever reach your irreducible entropy, right? So you can never hope to exactly reach your irreducible entropy, but what you can hope to do is get closer to it, right? So clearly, if you have finite data, right, so you're always going to be off from the irreducible entropy of text. So this is sort of the problem of scaling laws, in the sense of, I mean, it's not a problem of the scaling laws. It just, the scaling laws work in asymptotics, where they assume an infinite supply of data, but really we are, we're data limited. And so given the generative process, right? So the main contribution of the Chinchilla paper by Hoffman et al. Was they did a whole bunch of experiments, and they tried to fit several different ways these try to estimate these scaling exponents. And what they found is that for the transformer architecture, roughly alpha is equal to beta, and which is roughly equal to 0.5. So what this implies, or what this sort of means, is for the transformer, you need to scale tokens and parameters at an equal tandem, right? So let's say you raise the parameters to be for the transformer, you need to scale tokens and parameters in an equal tandem to be compute efficient, right? So what that means is, even if you had a super large model with many parameters, if you did not increase the number of tokens at an equal pace, you were undertrained and thus underperforming a smaller model that was trained on more data, right? So the overarching goal, obviously, is now that we sort of hit the limits on data, right, is to investigate architectures or sort of inductive biases that can potentially give us a better alpha, right? That can potentially give us a better scaling behavior in terms of the exponents alpha and beta, so that the intuition would be that for those architectures, you would need to reduce, or you would sort of hope to be compute efficient for those architectures. You would not need to increase your data at the same rate as increasing the number of parameters, right? So this means, right, so this is sort of the overall motivation, or sort of the overarching principle that we're shooting for. So like I mentioned uh, previously, that what we're starting to realize in a lot of these bigger AI labs, which train on pretty much the whole internet and all the books that have ever been written by humanity, what we sort of start to realize is that data is the true bottleneck. And there has been a lot of algorithmic progress on scaling large language models that have sort of contributed to some of these AI labs reaching the frontier. And that algorithmic work has focused mainly on compute efficiency, right? Compute efficiency, by compute efficiency, I mean, let's say, what are the algorithmic tricks that let me reach the same sort of training loss or same sort of quality with fewer or lesser compute. So the work that, different works that fall in this category, I would say, are things like better optimizers, for example, shampoo, soap, muon, so on. You have things like sparser MOEs. MOEs, for example, are a prime example of trying to spend less compute in terms of activated params, and then sort of reaching a better quality threshold. And then knowledge distillation would be another sort of way to not spend a whole bunch of compute and sort of reach a good better training performance, right? So this has been the work in the last few years. And what we're really interested in asking is the reverse question, right? Since data is the true bottleneck, right? What are orthogonal and sensible and clever ways of spending more compute with the same number of parameters, right? So in the sense that, since compute is what we know grows and data is the true bottleneck, what are some sensible ways of actually leveraging more compute? And of course, you could, not all flops are equal, right? So you could sort of take that compute and do something stupid with it. You could, for example, just, make the sequence longer or just increase the number of heads and so on. So there are ways, dumber ways of spending compute, and there are more sensible ways of spending compute. And this is sort of the motivation behind this work. So in particular, what we argue is the principled way, or the principled way of spending more compute in terms of leveraging the more amount of compute that we are sort of unlocking by building a lot of these large data centers. In that, I believe attention is key. And the reason for this is attention essentially is the mechanism that helps us capture or compute pairwise relationships between tokens, right? So it sort of is the way to create interactions between tokens. Whereas FFNs, since they operate pointwise, they sort of encode some knowledge / lookup table. They encode knowledge about the world, right? So when it comes to FFNs, I would argue that it makes intuitive sense that we want to be compute efficient in sort of memorizing stuff. And when it comes to spending more compute, we want to spend compute in terms of, enriching the attention mechanism. So I would argue that, sort of investigating sort of better attention mechanisms is the way forward for spending more compute in a sensible way. So attention is key, and in this sense, what we sort of realize is people who've trained a language model on, let's say, tasks, they sort of realize, for example, even if you have same model, two models with the same number of parameters, one thing people have noticed is deeper models are generally better in terms of performance on, let's say, coding and reasoning tasks, right? And sort of intuitively, what ends up happening is that if you control the same number of parameters, a deeper model has a better ratio of attention to FFN flops, right? Whereas the wider model, you would just be increasing the hidden dimension and just increasing your FFN flops. So compared to a deeper model that keeps repeating the transformer sort of loop, you are it's a way to increase your attention to a FFN flop ratio. And this ratio is also sort of increased implicitly in inference time compute or reasoning. So that's sort of what I would argue is, let's say, an indirect way of increasing attention to FFN flop ratio. And the reason being, the total attention flops in the sequence is n squared d. The total FFN flops is d squared n. So the ratio is actually n by d, right? So as you sort of unroll your inference time compute, you are increasing n, whereas your d is fixed. So you're sort of compensating for, in some sense, you're compensating for your fixed amount of attention flops that you could leverage during training. So all of those are great, and all of those are ways to increase attention to FFN flops. And what I propose in this work is to sort of revisit sort of the basic primitive attention. And the basic primitive of attention is pairwise relationships, where for a given node I and j, for a given pair I and j, we're trying to sort of capture their relationship to each other. And mathematically, the way to describe it is essentially it's called a one simplex in geometry. And then sort of the intuitive way to go beyond these one simplices or dot product attention is just start to look at triangles, right? Start to look at triples of attentions, or sort of what is geometrically called the two simplex between three nodes I, j, and k. So this is another sort of principled way of leveraging more attention compute, and it's sort of orthogonal to all these other methods. So you could sort of combine two simplicial attention with a deeper model and with inference time compute, and sort of And the hope would be that you're sort of getting, you're sort of equipping the model with richer representation, so you sort of do better at logical and reasoning tasks. So the paper, surprisingly, is old compared to LLM. So the original paper, which did not receive a whole bunch of attention, was from 2019. And to the best of our knowledge, this was sort of the first paper that seemed to propose looking at trilinear products, where instead of the way this works is, the standard transformer has a query. Given a sequence, we're trying to infer sort of a query vector, a key vector, and we essentially compute sort of a dot product attention, QK, between those vectors. And this was the original proposal in 2017 by the transformer authors. And then, to the best of our knowledge, the Clift paper from 2019 proposed generalizing this to three-way products, to trilinear products, where you sort of now have two keys, K and K prime. So you're essentially building like your attention matrix is no longer sort of a 2D matrix. It's now a 3D tensor. So it's going to be Qi, Kj, K prime, K, which one can. So the simplest way to do a trilinear product would be the simple trilinear product where you just sum up over the hidden dimensions the entries of the product of the entries of these three terms. And then one can do a softmax. So now the query I is now conditioning on both the tokens J and K. So you would essentially normalize not just in attention, we normalize over the rows, but here you would normalize the two axes corresponding to J and K. So you would sort of sum up the representations of J and K together, and this would give you your attention score. So the intuitive way to think about it is now you're sort of decomposing the attention I as sort of you're giving a different weight to pairs J and K rather than the same weight, right? So we can think of the standard dot product attention as sort of the diagonal of this tensor, where you're sort of giving the same weight to ij, but here you're sort of doing a finer grained decomposition of that diagonal, and you're saying, I'm going to give a separate weight to, depending on if J and K showed up together, I'm going to give it a separate weight. And if J and K prime showed up together, I'm going to give it a separate weight. So I'm sort of giving it a finer grained way to look at the world, right? And then the final output of the operation, attention operation, can be thought of as the sum over J and K. You take the softmax output, and then you have these two value vectors, Vj and V prime K, also obtained similarly. And you do a Hadamard product of the values, and you combine it with the softmax. And so this was proposed back in 2019 in the context of deep reinforcement learning in the original paper. And they showed that back then, this was before, so they had no results on natural language text. So they were essentially interested in pushing for deep reinforcement learning, like box world and logical reinforcement environments. And what they showed that this was a useful primitive, and that this outperformed dot product attention on logical sort of reinforcement learning environments. So the title of that paper is Logic and the Two Simplicial Attention. Right. So some challenges in incorporating this two simplicial attention into the modern day framework of large language models is we sort of use positional. So notice that this does not use any positional information, right? So in modern language models, we often use some sort of rotation position encoding, such as rope by Su et al., where the idea is you rotate the query at position I by a certain angle proportional to I, and you rotate the keys at position J proportional to J, and so it ends up that your dot product is then proportional to the distance between I minus J. And so then the challenge, of course, is how do you, right, so the challenge is, of course, how do you generalize to 3D? And notice that the simple trilinear form. So this sort of unlocks a whole rabbit hole in terms of trilinear forms, because in some sense, in standard dot product attention, dot product is in some sense the universal is a universal trilinear form. Whereas when it's a universal bilinear form. So you could sort of think of, you could represent, for example, uh, so this is sort of a geometric proof that there is a geometric proof that you could, given any bilinear form, you could find two vectors uh, sort of representing them as a dot product of vectors, but it becomes more challenging. So, for example, the determinant of 2 by 2 matrices you could just represent as the dot product of two vectors, where you have a1, b1, let's say a1, a2, b1, b2. So it's a1, b2, and a2, b1. So you could find the vector a1, b2 as one vector, and negative of a2 and b1 as the second vector, and then the determinant can be represented as a dot product. You could also think of like matrix products, like trace operations, and again you can show that matrix bilinear forms can also be represented as a dot product of two vectors. So clearly, dot product attention has not received too much crazy proposals in terms of bilinear forms, because dot product is in some sense universal bilinear forms. But it actually starts getting interesting when we come to trilinear forms, because what I showed before was the simple trilinear form where you just sum up the hidden dimensions and just multiply the entries. And this is actually not rotation invariant, right? And by this I mean, if I rotate the same query key by the same amount, so if I have the position qi, k1i, k2i, and if I rotate it by ri by an angle proportional to I, then this simple trilinear form is not equal, right? So the rotation invariance is not maintained. And why is this important? Because in bilinear forms, rotation invariance, it plays a key role in rope, right? So if you have two terms, you do not want, for the queries at the same position, for the query and the key at the same position, the rotation should not create any offset, right? So you want to have increasing offsets with distance, and for the same position, you want to have no change in the dot product. So then this sort of opens up this rabbit hole of trying to find trilinear forms that are rotation invariant. And one trilinear form that is rotation invariant that we found is determinant. And the way you would think of a determinant in this case is, let's say the query's keys are d-dimensional, then you would essentially do a determinant of 3 by 3. So this is three vectors, and you take the sub dimension of size 3. So then it becomes a 3 by 3 matrix, and the determinant is then defined. And the determinant is sort of the volume of the parallelepiped spanned by these three vectors. And the sum of these determinants is also a trilinear product. And one can show that determinant being rotation invariant makes applying rope rotation invariant in this case, right? So more precisely, for 2D vectors, it's the determinant of two terms would be a1 b1 a2 b2. So you get a1 b2 minus a2 b1. So in dot product attention, using determinants does not give you anything over dot product attention, like I said before, because you could just use the vector a1 b1 and b2 and minus a2 as sort of the two vectors, and the dot product of that vector is equal to the determinant of this, right? So the model, if determinant was the right thing to learn, the model would learn that dot product. But in the 3D case, actually, this determinant is quite different from the simple trilinear product. And so one might think that the determinant of this 3 by 3 matrix, which is like this 6 terms, which is A1, B2, I won't name the terms. So this looks like now we are doing 6 einsums instead of 1 einsum. And so there are some clever tricks apparently that one can use that Sai found, my co-author Sai found. One can use something called the Saras rule, where you can sort of compress this into two einsums, where you essentially take A1, A2, A3, B2, B3, B1, C3, C1, C2. So this can be accomplished by a sort of a roll. And so it's a PyTorch roll and 2 einsums. And with this, you can sort of sum up the determinants of the 3 by 3 matrices, and this is one way to be rotation invariant. There are also some other rotation invariant forms that are of interest, notably matrix rotation invariant forms, such as trace operators. So one problem with the matrix forms, and the reason we didn't include them, or the reason we didn't sort of do anything with them, is whenever you sort of compress a vector into a matrix, you're sort of reducing the dimension by, let's say, square root of d. And flash attention usually likes a very fixed, attention dimension, such as 128 or 256. So anything that sort of reshapes it into a matrix and incurs a square root dimension sort of may not make the best use of flash attention. So for this reason, we mainly focus on these two vector-based trilinear forms. So as I mentioned before, the simple trilinear form is 1 einsum and pretty easy to write. Determinant-based trilinear form looks like 6 einsums, but can actually be implemented as 2 einsums. And this has similar expressivity as the simple trilinear form, but with the added advantage now that we can add rope to the third tensor key, right? So when you're using the simple trilinear form, it does not make sense to add rope to the third tensor key, whereas with the determinant one, you can now leverage adding rope to the third tensor key. So of course, obviously one can argue that this is all well and good in theory, but then what about the cubic costs of attention, right? And for those who have been sort of around longer since attention was invented in 2017, I mean, back in 2020 and 2021, so this is like five years ago already, I remember people were sort of worried about attention growing quadratically with the sequence length, right? And people were, there were some proponents of LSTMs and GRUs and hybrid models. Like I remember Google had this hybrid attention model where they had an attention encoder and a LSTM decoder for, the reasons being that, quadratic cost is too much for attention, right? And all of Google Translate now, probably uses Gemini or something. So the lesson always is that compute eventually gets cheaper, and things like LSTMs and RNNs are not going to come back because they're more efficient, but rather compute is cheaper, so we want to leverage more compute in ways that make sense and that make the model stronger. So so of course dot product attention today is quite practical, but cubic attention on the full sequence today is still impractical. And so the way I propose to do it is, when dot product attention came out and people were sort of worried about the quadratic cost, there were many proposed methods such as, reformer, performer, longformer, linformer, SSMs, all of which sort of do linear attention. But the only linear attention method that sort of has stood the test of time is, I would argue, is local attention, where you sort of, The idea being very simple that, it's the simplest thing you could do. So every token, instead of attending to all the tokens before, it attends to a fixed, you know, budget of W tokens. So let's say you have a window, which is your local window size, and you are sort of, restricting your attention to the past W tokens. So this is clearly linear in the number of tokens because, W is a constant, right? So the reason this sort of works and is very powerful is that it has a receptive field that grows with stacking, right? So if you were to do some sort of chunking or blocking, you would not have that advantage. Whereas local attention it's almost like dilated attention, or if you read some of the WaveNet papers, it's sort of a similar flavor where the second layer gets 2 times the context of the previous layer, and so on. So if we look at the workload of a lot of the modern LLMs, that are open source, I don't know, like DeepSeek, Gemma, Llama, all the ones that are open source, none of these models actually use full dot product attention, right? So usually as much as 60 to 80% of all layers are actually local attention layers, right? So then one can start thinking that, okay, so local attention is actually being used, and local attention is great, and local attention has a growing receptive field, and right, so local attention is sort of the way to go. But then for a lot of these models, as we sort of start increasing the context length, right? So let's say Llama, whatever, when it came out, Llama 4, I think, had a 10 million context, and a bunch of these open source models have a lot of context length, right? So you are sort of, you want long context length because you want the model to think on its own chain of thoughts. So a model with thinking is better than a model without thinking. That's clearly true. But what is also clearly true is that a better model or a more powerful model with thinking is better than a less powerful model with thinking, right? So when you are thinking and you are unrolling the inference time compute on the chain of thought, you are no longer bottlenecked on your local attention layers, right? So your bottleneck starts becoming your global attention layers. So per your local attention, you can start doing more compute. And the way to do more compute is to capture higher order, relationships like three-way products, right? And then this the path forward that seems sort of fairly obvious now is then to do something like local to simplicial attention, or sort of local 3D attention, right? And the way we used to visualize attention back in 2020s and so on was this 2D matrix, sort of this heat map where you have this causal, the stride, which is sort of the area that the query can attend to. So that is now replaced by this tensor, right? So now we have this cubic diagram where the first axis represents the queries. So the second axis represents the keys, the first tensor key, and then the third axis represents the third tensor key, right? So this is like a 30 by 30 by 30 cube. And then what local 3D attention does, it slices out this sort of space within this 3D cube. And again, it has this property of growing receptive field on both axes. So on both the K and the K prime axes, you sort of start growing your receptive field. So you get the compounding effects of local attention. And right, so then the problem again now becomes an engineering problem where where we want to sort of leverage the tensor cores rather than CUDA cores. And then there's like multiple ways to tile it. So you could, for example, compute K and K prime, pre-compute those, or you could pre-compute Q and K and so on. So I won't go into the details. In the paper we produce essentially a Triton version And the PyTorch team has since kept iterating on it and improving on it. So I won't go into super details on those. But we sort of benchmark the latency of some choices of these attention windows. And so, for example, if W1, what we find is for a given amount of flops or for a given amount of uh, uh, compute budget, let's say, which is W1 times W2, it always makes more sense to use asymmetric windows than symmetric windows. And the reason being the asymmetric window can sort of carve out, uh, at least on one axis, it has a bigger receptive field, right? So I guess until the day we see sort of 512 by 512 windows, which is not yet here. What we are currently able to use is something like 512 times 32, which has reasonable sort of latencies, and then something like 512 times 64 gives you better quality, but has, let's say, 2x the latency, and so on. And so this is sort of the latency constraint. And what we see is that because this is sliding window, right, there comes a point in terms of, because full attention, right, you still need to do full attention for your global attention layers. And there comes a point where the cost of this of trilinear attention is dwarfed by the cost of full attention, because the cost of full attention is growing quadratically, whereas the cost of trilinear attention, because it's windowed attention, is not growing quadratically. And I believe we show in that paper that that threshold was something like 32K or 48K, something in that regime. So that was our previous implementation, but people have subsequently improved the PyTorch code. So probably that threshold, that crossing will come sooner. And what that means is anytime your chain of thought or whatever crosses 32K, then you're getting all this free compute that you can tag on to your local attention that you should be using. So how can we sort of measure in a principled way the impact, or sort of how can we argue for this architecture, that how does this architecture move the needle correspond compared to a transformer? And for this, again, I come back to scaling laws, where the idea is that we want to find models that are more token efficient, right? Because our data set is sort of fixed, right? So we can't be doubling the data every time we scale the transformer, right? Because we don't have high quality data anymore on the internet. So then this can be interpreted as, how can we make a model more token efficient? And the way to do it is, let's fix the d axis, right? Let's fix the data axis. And the data axis being fixed means that you're modeling, you're trying to find for a particular amount of data a model that has a better exponent, scaling exponent alpha, right? And this scaling exponent alpha may or it's sort of like, I would argue, is one can do this for the whole training set or the validation set, but as our training grows larger and larger, you won't see as much impact on the training loss. So you will see some marginal improvement on the training loss. But two models at the similar training loss performance can have very different behavior on the different kinds of tasks. So for example, one model could be very well in logical reasoning tasks, and one model could be very well at tasks which require more knowledge, and so on, right? So it's sort of maybe more important to sort of do this on a per task basis, where you decompose, or on maybe per task category basis, where you sort of have a scaling category for reasoning tasks and scaling category for knowledge tasks. And right, so an asymptotically more token efficient architecture should have a higher alpha, right? And so we did at Meta, I mean, for the way we did scaling laws was, under a log linear assumption where you can sort of take logs on both sides and you plot the log loss on one axis and plot the log parameters on another axis. And if you have some, if the irreducible loss is small, you can sort of approximate this as sort of a linear curve, and you can measure the slope improvement. So at Meta, we only had the time to, we wanted to do it on more models, but unfortunately, Meta is a bit fast moving. So we did not have the time do to scale the model to larger than 3.5B active. But the models were fairly large enough that we were confident that this is not, it's not a fluke. And then the total parameters, so these were like very sparse DeepSeek style models where you have, total parameters were like 176B, 100B, 57B. And we had the same token budget for all three models, and we, trained them to for the same number of steps, right? I think it was like 2 epochs or some amount of epochs. So the folks there had figured out the maximum number of epoching you can do on an MOE model or whatever, right? And so that was that. And then so the idea then was we try to measure whether this changes the slope on different tasks, right? So it gives you some slope improvement on the training loss, but what we see more clearly is, for example, on problems like GSM-8K or on data sets like GSM-8K, the slope improvement is, by the slope improvement I mean that the larger model should have a higher magnitude of improvement than a smaller model, right? And we sort of see that trend, at least in the log linear plot on GSM-8K, MMLU Pro, and to an extent on MMLU and MBPP. And right. So what I would have liked to do, but we did not have the time to do at Meta, is sort of take it all the way and show that combined with inference time compute, you still get better wins. So one way to formulate this would be maybe there are classes of problems where the standard transformer needs X amount of inference time tokens to unroll to solve a particular problem, whereas for this trilinear attention, that number is asymptotically smaller, right? Well, so we didn't get the time to do that at Meta, but anyway. So this alpha here represents the slope. So on GSM-8K, we see that the slope has improved by 18.5%, and an MMLU Pro has improved by 20%, and a smaller improvement on MMLU and MBPP. So in some sense, sort of encouraging, because GSM-8K and MMLU Pro are less saturated than the other two. So seems quite promising in terms of the next model to scale. And the original implementation was in PyTorch. This was my naive implementation, and then Tim Chow did an awesome job writing it in Tim Chow, and others wrote it in Triton. And then you can follow this blog post by the PyTorch team. They've sort of carried the torch forward and made this even more efficient by rewriting it in TLX. So yeah, this is sort of the high level view. I'll leave some time for questions, if any.
Thank you so much for the amazing talk. If anyone has any questions, feel free to unmute and ask.
Yeah. So yeah, that was a really interesting talk. I was wondering, like, one of the advantages of the original transformer and attention architecture was that we could parallelize it much more efficiently across multiple GPUs. So when you were implementing the trilinear kind of attention, did you face any like problems with or less efficiency uh, when you were training it using a multi GPU kind of setup?
Right. Yeah. So it's trilinear is also parallelizable, right? So if we look at this formulation, right? So it's you do not have to. So the parallelization. So LSTMs suffered from the problem that to compute the ith representation, you need to know the I minus 1th representation, and so trilinear also does not have any sequential dependencies, right? It's to compute the ith representation, you do not need to have computed the I minus 1th representation of the trilinear attention, right? So you can still parallelize it. The challenge with trilinear attention is slightly different. The challenge is that modern GPUs are, they leverage tensor cores, so they like matrix multiplies, so they like matmals, right? And this is not exactly this is not a matmal, right? So this is sort of like if you think of k and k prime, let's say you pre-compute k and k prime, that's sort of like matrix multiply, but without the reduced sum, right? So this is not a primitive on modern GPU tensor cores. I think that's sort of the biggest challenge. Rather than being able to, I think parallelization is fine. Yeah, so you don't have sequential dependencies. The challenge, I think, is more in terms of leveraging tensor cores as opposed to CUDA cores for the GPU. I'm not certainly an expert on that, so the PyTorch team has. I mean, I would recommend you to go read the blog. They have gone super deep into the details on
Y-
on
yeah. Thanks.
Mhm.
Yeah, I was kind of like thinking about the matmal as well. Like, were you using like Khatri Rao, that kind of thing um to simulate kind of matrix multiplication? But yeah, I'll check it out. Thanks.
Right.
Yeah, so I have another question. So you constructed the rotation invariant trilinear form. So
Mhm.
do you, it is generalizable to higher orders simplicials, like if you go 3 or 4?
Right. Yeah, I think so. I think determinant is because determinant is rotation invariant, right? So if you take the determinant of higher order 4 simplices, right? So 4 simplices is 4 by 4 matrix, right? So if you rotate each of the axes by the same angle, right? The determinant captures the volume of the parallelepiped spanned by these 4 vectors, right? So that volume remains unchanged if you rotate the 4 vectors by the same angle, by the same amount, right?
Right. Yeah, thanks.
So determinant is the principal rotation invariant form. Yeah.
So if you don't have any other question, we can conclude the session here.
Thank you.
Thank you so much for the amazing talk, and it was really
Thank
insightful.
you.